All right, folks, this is the one of my favorite optimization problems. This is what I call the smallest container problem. One of the things I really like about this problem is it's a very realistic sort of problem that you could see in the business world because this is in an economic problem. What's happening here is, when manufacturers, when businesses sell products, especially liquid products, they have to put it inside of a container, like Campbell's soup. They put the soup inside of a can. If they could sell you the soup without having to put it in a can, I'm sure they would, because the problem with the can is that usually it's metal and it costs them money. So they not only do they have to pay to make the soup, but they have to pay to make, well, they probably don't make the can. They probably contract it out to somebody, but maybe they do make the can. But the thing is, the can itself is not being consumed. You're not eating the can. The whole purpose of the can is simply to transport the soup, the liquid, from where they make the soup to the store and then to your house, and to be stored in your pantry until you open the can and put the soup in a bowl to microwave or in a pot to heat up. So the can itself, ideally, businesses will spend as little money as possible manufacturing the can and using the can. And one way that they can spend as little money as possible on the can is by making the can out of as little material as possible. This is also the case for if you're not a soup eater. Well, think about soda. You know, soda oftentimes comes in a can, and the can, you're not consuming the can. Ultimately, well, we used to just throw out the can. Now we try to recycle the can or reuse the can for something else. But I think we can conclusively agree that the can itself, its only value is to carry the product from the manufacturing plant to where you are when it comes time for you to consume it. Okay, so we would like for this can to be made out of as little material as possible, but still be able to carry the amount of the product that they're selling to you. Okay, so I call this the smallest container problem. And when I say smallest container, I don't mean smallest in volume, I mean smallest in material. Now, when we think about the material that a can, if you look at a soda can or maybe a soup can, right? The can is the outside of the product, right? And mathematically, geometrically, that is the surface area of the can. The volume, the insides of the can, presumably that's where the soup or the soda or whatever the product is, that's where that's being carried. So we're not necessarily concerned, we're not necessarily calculating what's inside the can. We're concerned with the outside of the can, which is the surface area. So basically what we're doing in this problem is we are minimizing the surface area of a cylinder, of a can. So the question says a manufacturer needs to make a cylindrical can that will hold 92 cubic inches of liquid. Now that's kind of a big can, okay? I think it's close to a liter. So now we're talking kind of a little bit of a bigger can than a soda can. Determine the dimensions of the can that will minimize the amount of material used in its construction. And you may not know this, but I'm going to go ahead and give you the formula for the surface area of a cylinder is 2 pi r times h plus 2 pi r squared. Okay, and let me explain why. This is pi r squared. That's the area of a circle. That's the top of the can and the bottom of the can. Since there's a top and a bottom, we're going to multiply it by 2. Now this right here, this 2 pi r times h, this is actually 2 pi r times h. That's actually a rectangle. And you might say, well, I don't see any rectangles in a can, Mr. Ryan. Well, if you cut off the top and the bottom and you only had the side of the can, if you were to perforate it and cut it down the center and then fold it out, it actually would look like a rectangle. Basically what you do with is you take a rectangle, right, a rectangular piece of metal, and you basically turn it into a circle, and now it's a cylinder, right? And so the outside edge, the sides of a can, if you were to open it up, would actually be a rectangle. And so if you understand that, a rectangle is base times height or length times width or whatnot. And actually, you know, the height of the can is the distance from here to here, and that's the height of the rectangle. But this length of the rectangle, or the base of the rectangle, is being turned into a circle. And therefore, it's actually a circumference. It's the circumference of a circle. And so circumference of a circle is 2 pi r. And therefore, the outside of the can, the sides of the can, are circumference times height, or base times height. Okay? So 2 pi r h, and then add to that 2 times r times pi r squared. That's the top and the bottom of the can. Okay? So that's the surface area. And now, so this is actually the formula that we want to minimize, because we want the surface area to be as small as possible, right? But here's the problem, is that in this formula, go ahead and get rid of this, and we'll get rid of this and this. The problem here is that we have an r and an h. We have two input variables. Radius, that's the radius of the cylinder, as determined by the radius. See, if we have a can here, well, let's say this can. If we were to go to the center of the top of it, the distance from the center of the top to the edge, that's the radius of the cylinder. Okay, so whatever that, and then the height, sorry, I should have told you the height also. The height is the distance from the, if you were to set the can on a table and then measure it from the table all the way up to the top of the can, that's the height of the can. So that's the distance from here to here. All right, so we have the height of the cylinder, and then we have the radius of the cylinder. Okay? So the problem with that is, we've already said in optimization that we can't optimize if we have two input variables. We need to somehow or another relate the two variables to each other. We need to relate radius to height so that we can eliminate one of the variables, and then we can use single variable calculus to optimize or to minimize the surface area. Okay, so now in the problem, we were given some information that will help us make that relation. And that is that the can is supposed to have 92 cubic inches of liquid. Now, 92 cubic inches, that's a volume. And so if we go get the volume formula for a cylinder, which I happen to put right here, the volume of a cylinder is pi r squared times h. What we can do is we can put that 92 in for V. And so now we have 92 is equal to pi r squared times h. And now we have an equation that relates r to h. Now we need to rearrange it a little bit. I want to eliminate h, if that's okay. So I want to solve for h in the volume formula. Well, if I want h all by itself, I'm going to divide by pi r squared on both sides. And over here, it's going to cancel pi r squared, and now h is equal to 92 over pi r squared, which can now be put in for h over here. So now, step one is to identify a formula, right? Step two is to bring the formula down to a single input variable. So now it's going to be surface area is equal to 2 pi r times 92 over pi r squared plus 2 pi r squared. 2 pi r squared. So this is now our formula for surface area in terms of radius only. Now this is the surface area of all possible cylinders that have a volume of 92. Okay, this is not all cylinders. It's the whole family of all cylinders in the universe that have a volume of 92 cubic inches. Well, I mean, you could make it 92 cubic centimeters if you want, then it'd be smaller. But anyway, so let's see here. So our next step now is, well, before we go anywhere, look, we can simplify this. We can actually cancel one of these r's right here. We can also cancel pi. So let's clean this up, shall we? I'm going to cancel one of the r's because r divided by one of these r's is 1. Also, pi divided by pi is 1. And 2 divided by 92 is 184. So now I have surface area is equal to 184 divided by r plus 2 pi r squared. Now, I happen to know that I'm going to have to find the derivative of this. So because I'm going to find the derivative of this, or you know what, well, you know what, we'll go ahead and use the graphing calculator for it, but I will show you what I would do if I was going to find the derivative of this. In fact, we'll go ahead and do it, and we'll do it with the calculator also. My surface area, this r to the first power in the denominator can actually come out of the denominator, and I would have 184 r to the negative 1 power. And then it'd be plus 2 pi r squared. So now the question is there an interval over which the radius, okay. Step 3 is we have to identify an interval for the formula. And we've already said in previous videos that geometrically, radius distances cannot be negative. So that means that r cannot be negative. Now, also, because r is in a denominator by itself, just r, it also cannot equal 0. But it can be anything larger than 0. So we know that it's going to be an open interval at 0. We cannot plug 0 in. But then the other thing is this is, well, this is always positive. This r squared is always positive, and therefore it looks like, and it's being added, so it looks like r can be anything. So really, our interval for r is from 0 to infinity. Okay? And so now the last thing we have to do is we want to minimize this formula here. Okay, so the derivative, SA prime, is going to be negative 1 times 184, which is negative 184, times r, reduce the power by 1, so that's negative 2. And now the derivative of 2 pi r squared is 4 pi r. Okay? And now I'm going to clean this up. I'm going to go SA prime is equal to, this r to the negative 2 can now go into the denominator. So I have negative 184 over r squared, so that's always going to be positive, plus 4 pi r, and that's going to be equal to 0. And so now I can solve this algebraically. I can add 184 over r squared to both sides, and now I would have 4 pi r is equal to 184 over r squared. And now if I multiply by r squared on both sides, okay, I get 4 pi r cubed is equal to 184. I'm going to divide by 4 on both sides, divide by 4, and now I get pi r cubed is equal to, let's see here, 4 goes into 4 and 24, 46. All right, so 46. Divide by pi on both sides, divide by pi, and now I get r cubed is equal to 46 over pi. Last step, I'm going to do the cubed root of both sides. That's going to cancel my cubed, and r is equal to the cubed root of 46 over pi. Now, that's not very meaningful because I guess I can set the machine to a distance of cube root of 46 over pi. But mentally, up inside my head, I would like to know what length I'm dealing with. So I'm going to go get a calculator, and I'm going to key in the cubed root, oops, wrong button, the cubed root of 46, whoops, divided by pi. and I get 2.4464. This is approximately equal to 2.4464 inches. This is the radius when the derivative of surface area is equal to 0. We know now we can make our table, and so we'll have radius and we'll have surface area. Okay. Now, we are not, well, we can put 0 in, but we can't put infinity in. See, the reality is we actually don't have an interval. We don't have endpoints. The endpoints simply go from 0 to infinity. And we can't actually plug 0 in because it's in a denominator, and we can't plug infinity in because infinity isn't really a number. And so what we're going to need to do here is we're going to have to put in 2.4464 and then plug this into the surface area, and then create a sign chart for the derivative to determine whether this is a minimum or a maximum. So let's go ahead. This is our last step. We're optimizing. We're making our table, but we only have one critical value, 2.4464. And so we're going to plug that into surface area right here. So we're going to do 184 divided by the radius. The radius is 2.4464. All right. And then we're going to add plus 2 pi r squared. 2 times pi, and then the radius, 2.4464 squared. And then we're going to press enter. Whoops. And we get 112.817. 112.817. Now, to find out whether this is an absolute maximum or an absolute minimum, now we're going to make a sign chart for the derivative of surface area. So we'll do surface area prime, and we'll draw our R axis, actually. We only have one critical value for surface area, which is 2.4464, right? And now we're going to plug in a number smaller than this, which is 2, and we're going to plug in a number larger than this, which is 3, and we're going to plug those into the derivative to find out whether the derivative's surface area prime is positive or negative on either side of this critical value. So if I plug 2 into, here it is, into this right here, here's our derivative right there. So we got to do negative 184 divided by r squared. Well, r in this case, we're plugging in a 2. 2 squared is 4, so I'll put in a 4. So negative 184 divided by 4 plus 4 pi r. That's 4 times pi times 4. 4 times 4 is 16. R is not 4, r is 2. R squared is 4. Plugging 2 in. So 4 times 2, which is 8 times pi. So 8 pi. And I get negative 20.8672. So that's a negative value, so we'll put a minus there. Now we're going to plug 3 into the derivative of surface area. 3 squared is 9, and then over here it would just be a 3. So we're going to do negative 184 divided by 9 plus 4 times pi times 3, that's 12 pi. 12 pi. And I get positive 17.25, and that's a positive number. And because surface area goes from negative to positive, that makes this a relative minimum. And because it's also an absolute value from optimization, it makes it an absolute minimum. So we have succeeded in showing that, that the correct radius for minimizing the surface area of this can is 2.4464 inches. Now we need to know the height. And to find the height, because the question says determine the dimensions of the can. So we'll go here to 92 divided by r squared. And so I'll just do 92 divided by pi r squared, divided by parenthesis pi, and then r is 2.4464. I'll square that, and I get 4.8931. So height is 4.8931 inches. Okay? And so if you were, so this company now can know that they need to calculate or to determine what size the can they should make. They can set a machine now to produce a metal, if it's a metal can that will have a height of 4.8931 inches and a radius for the top and the bottom of 2.4464 inches. And I know that this is probably one of the tougher ones that you would see, but it's really worthwhile practicing. What I would do if I were you is, if you're still sort of hazy, is go back through this video a couple more times, work out this problem with me, write out all the stuff that I do, and you'll get a lot better at this. And then find other problems. You could even take the same problem. Why don't you change the volume and then find out the size of a new can that has a different volume, and that can help you become much better at optimizing this sort of thing. Okay? All right, well, that's all I have for now, and I hope this helps a bit and makes you better at calculus.